welcome back. So now that you are already introduced to various technical specifications of an industrial robot that determine the performance and capabilities of an industrial robot. So now in my today's lecture I would stress upon repeatability test. This is one of the most desirable tests that is applicable or relevant to any industrial applications. Other important tests are velocity characteristics, drift, path repeatability or path accuracy, cornering deviation, etc. So now without much delay, so let us start with today's lecture where I'll be focusing more upon repeatability test. That is something that you have also seen in the data sheet that I have shown in my earlier modules. So let us begin. So yes, before we actually get into repeatability test, one more parameter which is very close to repeatability is accuracy, and that also is very much desirable, and that is quite a lot of time is also mentioned in the data sheet of some of the robots. So let me also introduce this along with repeatability here. So pose accuracy, pose is basically position and orientation. So pose accuracy is the difference that occur between commanded pose and the barycenter of the attained poses. So you see, you have a commanded robot to go to a certain place, okay, and then your robot goes to a different place somewhere, okay. So it is the difference between the commanded pose, that is this one, and the barycenter means the almost the centroid, the most of the point where it lies. So between that and this, so whatever is the distance is known as the pose accuracy, okay. And similar in case of position, it is easily visible geometrically, but in case of orientation, it can be very much analogous to this, in which you have a commanded orientation and the attained orientation in terms of angles along the each axis, okay. So this is what is accuracy, pose accuracy. And what is pose repeatability? It is basically the fluctuations in the attained poses for a series of repeated visits, to the same commanded pose in the same direction. So we'll discuss more upon this in this lecture. So I'll discuss this very much thoroughly now. So these are the errors, and they are mostly caused due to internal control definitions. Examples: controller gains, model parameters. If the model is not proper, which is there with the controller, or after the assembly the model has little bit deviated, this error may be there. If you command the robot to go to a certain place and it goes to a different place, there may be some deviation in between them, okay. So that is the model parameters. What were the model parameters, if you can recall? That is moment of inertia, mass, okay. So center of location of the mass. So these are some of the models which are there with the controller already. So that defines the dynamic equation of motion of your robot. So that is model parameter I mean here. And the controller gains, that is, you have seen in the controller module also that what are controller gains. They are basically proportional, integral, or the derivative gains. So if those parameters are not tuned properly, in that case also this deviation can occur, okay. So others are kinematic transformation errors or coordinate transformation errors. If you have not calibrated your system well, this error can also happen. You need to know the precise dimensions of your link offset, joint offsets should be known, okay. So those are the DS parameters. If they are not precisely calibrated, this error can also occur, okay. The difference between the ideal dimensions with the robot arm fed to the controller, that is the DS parameter which is fed to the controller, and the real dimensions of the robot after manufacturing, there are some differences between them due to the manufacturing error or assembly error. So it is mostly caused due to this, okay. And due to the mechanical faults, basically clearances, if they are there, hysteresis, some friction, can be some temperature deviation, if the links are very long and you see some expansion in the link due to the change in temperature, so this can also cause this type of error, that is pose accuracy or repeatability errors. Okay, so repeatability test is precisely defined in the standard called as ISO 9283 in 1998, and it is still getting revised and updated every few years, and now this one is the one which is actually being followed. Before we actually do such test, there are various guidelines before actually getting this test done. So the robot should be mounted in accordance with the manufacturer's recommendation. Basically the leveling, alignment, functional tests are to be done. If it is to be mounted on the flat floor, or it is to be mounted on the vertical wall, or on the ceiling, maybe on the inclined plane. So if that is done, it should be precisely defined by the manufacturer, and the test people should actually follow that particular recommendation which is given in the manufacturer's technical specification sheets, okay, or on the test sheets what are recommended by the manufacturer. Okay, so next is the test should be preceded by an appropriate warm-up operation. Why this is important? You know, the joints or the links, they take some time to actually catch up with the actual dimensions due to the temperature changes. Okay, or when it is actually working, the temperature may be different at the environment where it is working. So there are certain guidelines on the temperature also, and robot, when it starts, it takes some time to stabilize on its temperature. Okay, so that is why robot is made to run for few minutes, few hours before the test should start. Okay, it is specified by the manufacturer only. Okay, so normally the tests are done by a third party, not by the user or by the manufacturer. Okay, so they are some they follow some specific guidelines. So there are guidelines given by the testing organization and by the manufacturer. So it depends what is more important and how it should be done. It depends on the guidelines given by both of them. Okay, so normal operating condition for tests are stated by the manufacturer, that is the power fluctuations, how much power fluctuations can it tolerate. Okay, so that is given. Disturbances in the load, how much additional load, if there are multiple things which are clubbed to the same line, same power line, how much disturbance that it can take, how much load disturbance it can take. Maximum safe operating limits are all defined by the manufacturer. So a test organization should always follow the guidelines given by the manufacturers. Okay, so yes, the other environmental conditions are also stated, like temperature, relative humidity, electromagnetic and electrostatic fields, radio frequency interference, atmospheric contaminants, and altitude limits. So all these are mentioned. Okay, and ambient temperature, this is defined by the test organization. This is a standard condition for the test. This cannot be defined by the manufacturer. So they do all the tests at this temperature, that is 20 degrees centigrade, and it shall be maintained at 20 plus minus 2 degree. So this is the deviation. Deviation should not be more than plus or minus 2 degrees. The robot should be protected from drafts. Drafts means if there may be in the industry there are forced air draft, so that air should not directly fall upon the robot. So it should be protected from drafts. External thermal radiations like sunlight, any heaters if there are around, so it should be protected from all of them. Okay, the pose data should be measured in the measurement device coordinate system. So that is with respect to the device coordinate system, you can measure the pose, that is the position and orientation of your robot, or with respect to the robot's base coordinate system. With respect to the robot's base coordinate system, the relationship between them should be well established by the measurement also. Okay, so only two coordinate systems which are important here One of them is the robot's base, about which robot's end effector is normally found out using forward kinematics or anything, okay, or by the external measuring device. And the second one is the robot's measuring device, the measuring device coordinate system, okay. So with that only you can measure the end effector position and orientation, okay. The measurement device characteristics should be good enough so as to represent the data being measured. So if you have to measure something in millimeters, so your measuring device should be capable of measuring much below that millimeter, maybe sub-millimeter distance it should be capable of measuring, okay. So there are specific guidelines on that also. I won't go much deeper into it, but you should understand why it is so. So if you have to measure a millimeter, your scale should not put its graduation in terms of centimeters. That is straightforward and simple. So the device should be well calibrated with the following parameters taken into account, that is the instrument error, systematic error and the calculation error. All these three types of errors should be well calibrated and those parameters should be taken into account while using that device. The tests shall be executed with a load that is equal to 100% of the rated load condition. If the manufacturer says this robot can take a payload of 250 kilograms, so the test should be carried out with 250 kilograms mounted at the end effector, okay. And same with the mass, center of gravity location, moment of inertia and etc. So everything should be as stated by the manufacturer. So the test, if you are making it move in a trajectory, the robot should carry that much of load all the time, 100% of the load while it is moving in the trajectory, even if it is stopping. So all the tests like stopping distance should also be calibrated using that 100% of the rated load conditions. So it should be measured with that kind of load in place, okay. So the mass and position of the measurement device should be considered as the part of the test load. If the test device is mounted on top of the robot end effector, so that mass should also be accounted for, okay. If it is a 12 kg payload robot and you have another 1 kg that is the measuring device weight, so you should not go beyond 12 kg. So the total mass should be accounted for. All the pose characteristics shall be tested with maximum stated velocity. If the robot can move with 2 meters per second, if the robot data sheet says so, the repeatability test should be carried out with the maximum stated velocity. The robot should start with 0, pick up the maximum speed and again go back to 0 at the maximum velocity which is stated by the manufacturer or what your controller can achieve between two endpoints. A minimum number of commanded pose shall be used, okay. You should not command more than a single command in order to go to a single place. It may be through a teach pendant, that is through teach and repeat thing it can be done. You teach it to go to a place and the robot repeats it to go to the same place. It can be in a teach repeat format, or it can be commanded manually using manual data entry, or you just define set of points where a robot should go while this test is to be carried out using some offline programming technique also. So all these can be considered as the commanded poses, okay. Other tests can be performed simultaneously, like if at all you are doing repeatability test which takes a robot to a predefined pose, okay. We'll discuss upon the predefined poses now only in this lecture only. So coming back to this, so other tests can be also performed simultaneously which support same type of poses in order to do that, like path accuracy or velocity tests that are also done with the same set of points, similar set of points. So those tests can also be done, okay. Okay, so this is what is defined where a robot should be taken to when this type of test is done, like repeatability test. So these are the definitions of different positions. So It basically defines a cube or a rectangular parallelepiped. Okay. The TCP is moved to the designated corners of one of the cube planes. In case of 6 degrees of freedom, you can only use one of the planes, which is marked over here in gray color. There can be other diagonal planes or other planes of the robot as well, of the cube as well. Okay, like you can have a diagonal like given by connecting these two, this and this. Okay, there can be one diagonal plane that goes like this, or it can be yet another diagonal plane like this one. This can also be one of the plane. So all the other planes are not very important if it is a 6 degrees of freedom robot. So in case of 6 of robot, only the one which is shown here in gray color is considered. Okay, so other planes are C1, C2, C7, C8. C1, C2, C7, C8. So this is the one which is of our interest because we are mostly dealing with 6 DOF robot, not like a SCARA robot. Okay. Another plane could be C2, C3, C8, C5. That is C2, C3, C8 and C5. Okay, this. Got it? So you understand there are 4 different planes that can be used. Okay, and you have to make almost 30 repeated cycles. You have to take the TCP to each of the points 30 number of times in order. So it can be taken in order. So there is one more point which is very much of an interest, that is the point of intersection of diagonals, that is the centroid of this cube. So this is the first point from where the robot actually starts moving. It goes to P1, then C1, C2, C7, C8, and it has to do that for 30 number of cycles. Okay, so starting point is P1, that is the intersection of the diagonals. The test path should be linear. It should go from one point to other in linear or in a circular way only. So normally linear is preferred. Okay, all the joints shall be moved. So while moving between any 2 points, all the joints of the robot should move. It should not happen that one of the joint remains stationary while others are moving. Okay, while moving between 2 points. Okay, the points are located at a distance from ends of the diagonals which is equal to 10 plus or minus 2% of the length of the diagonal. If you see you have a total length of the diagonal is something like this, so your actual point where robot is taken is something like this. So you can go from here to here. Okay, so that is what is marked over here. Okay, C7, that is 10% of the diagonal. So that is here 10% plus or minus 2%. So this is what is your 10% of, if this is your total length L, so it is 10% of total length. So that can be from here. So effective points are this. So this is where your robot will actually go. Got it? So this is where your robot will actually go. Okay, so out of this total space which is marked by this cube, so the 10% deduction is there along the diagonals where you actually take your robot while doing this test. Okay, so the effective points are P1, P2, P3, P4, P5, which are marked here by me just now. Okay, so the cube shall be located in the workspace with the greatest anticipated use. Okay, so this cube should be located in the workspace of the robot where you see your robot is actually to be used, and you should cover the maximum workspace. Okay, so as to test your robot properly. Okay, and the edges of the cube should be aligned to the robot's base coordinate system and the maximum allowable volume. Okay, let me just remove myself so that you can see it. Okay, so the cube should be located in the workspace with the greatest anticipated use, and the edges of the cube should be aligned to the robot's base frame. Okay, so you see robot's base frame is marked here. Okay, so the robot's base frame should be like this, and your robot may be mounted something like this, and this cube should be in this workspace. Got it? Okay. Okay, so the positioning accuracy of the robot is defined as, there are different parameters. Let me just talk about one by one first. Okay, so this is the actual point where it is commanded to go. Got it? So this is given by OC, and your robot actually goes to a point which is here, and there are different points where the robot goes. Okay, so every time you command your robot to go to this place, okay, which is marked here as red, let us say, so it goes to the location which is here. Okay, so these are the points. Okay, so you just take mean distance of this, so that is given by x bar. Similarly, along y it is y bar, along z it is z bar. Okay, so you take the distance which is known as APP, so that is given by AP, this is the one. Okay, so that is x bar minus xc. Xc, yc, zc are the commanded location along xyz. Okay, and x bar, y bar, z bar are the basically that defines the barycenter of this. That is, the barycenter is B over here. So barycenter of this. So you see APX is nothing but this one, APY is this one, APZ is this one. Okay, so x bar is basically mean of all x. If it is n number of times it is attempted to go there, normally it is 30 or more than 30 can be definitely done. Okay, so it is 30, so you take mean of that, so that is x bar. Similarly along y, similarly along z. So commanded minus mean, commanded minus mean. Okay, commanded minus mean, so those are this. Okay, so that is over here, you just take square and take the root, so it takes you to AP. So this is this one. So x bar, y bar, z bar are the barycenter of the cluster of n attained position for the same commanded pose. So over here only the position is shown. xc, yc, zc are the coordinates of the commanded pose, that is this one. So this is your basically positioning accuracy, position accuracy. Okay, xi, yi, zi are the coordinates of the ith attained pose, that is basically used here in order to take the mean, that is the center of the whole of the cluster, that is the barycenter. Okay, so this defines your positioning accuracy. So mathematically orientation accuracy is also defined in the similar way. However, it cannot be shown geometrically in a way like this. So you can have mean orientation. If you command it to go to a particular orientation, so it just deviates from a little bit from that. Take mean of all of them, 30 attempts altogether, that goes here, and commanded angles can go here. Okay, so that actually goes here, and then you take positioning, that is the orientation accuracy. That can be done mathematically in a similar way. So with this we'll stop for the positioning here. Let us go to repeatability here again. Okay, so basically repeatability is defined by RPL is equal to L bar plus 3 times of SL. So what are they? I'll define here. So what is L bar? L bar is nothing but 1 by mean of all Li. And what is Li? Li is now xi, yi, zi are the, in any particular ith attempt, robot goes to xi, yi, zi location. X bar, y bar, z basically defines this point, that is the barycenter point. So distance from the barycenter for any ith attempt is taken here along x, along y, and along z. Okay, so this gives you mean of all the squares, sum of squares, so that gives you Li. Okay, so that goes here. L bar is like this. Okay, that is defined like this. So Li is defined like this. So all for each and every attempt you calculate Li, take mean of them, so that comes here. So SL is basically, you take sum of all I is equal to 1 to n li minus l bar square divided by n minus 1 square root of that. Okay, so it is similar to root mean square of the distance, so that is SL. So that goes here, and L bar is calculated here only. So this is your L bar that goes here. SL is defined here, so that goes here. So total position repeatability is defined like this. Got it? Similarly, the orientation repeatability, you don't have the term which is like this. So that is calculated along each different axes also of the coordinate frame. So that is along x, along y, along z. In robot terminology, it is also mentioned as A, B and C axes. Okay, so it is nothing but 3 times of SA, and again SA is defined as AI, that is the ith attempt, that is the angle attained along x. A bar is the mean of all the angles it has taken while attempting in multiple number of times. So root mean square is taken like this. So that is 3 times of that is basically your repeatability along A, repeatability along B, repeatability along C axis. So that is defined. So these definitions are precisely given in the ISO standard, that is ISO 9283 1998. The relation is also valid when the distance are not normally distributed. It need not to be normally distributed. It can be totally oriented all along the same direction. Okay, so even then it is valid. Okay, so it need not to be normally distributed. So this is what basically defines the repeatability. Okay, so let me just show you one case when we had a parallel robot and we did it for that. So let me just take you a visual walkthrough how that was done. Okay, so this is the robot. Okay, so this is a serial robot basically. I am not going to measure the repeatability of this serial robot, which is actually the KUKA robot, which is shown here. Okay, I'll just move a bit now. Yes. So yes. So this is a parallel structure which is shown here. This is a parallel robot. Okay, where you have you have an actuator here, actuator here, actuator here, and there are total 6 actuators that move the top platform. I'll show you moving this platform also, how it is moved. So effectively I have fitted this robot at the end effector of the serial robot just to mount it, and there is no specific reason. And you see you also have a load cell which is here that can basically take up the load, and you can it precisely tells you how much load is carried by this end effector, that is the platform of this robot which is mounted here. You see you have a controller over there that basically moves this platform. Okay, so overall this is the arrangement that I have shown here. Okay, closely you can see it like this. Okay, so these are the different links that actually move this top platform which is here. Okay, different angles I have shown here. Okay, so this is how now it is arranged, fitted to the wall. It is similar to fitting the robot to the wall, and robot is mounted like this. I want to check repeatability when it is mounted in this way. You see, so this is your top platform. So that is what is going to move. That will remain stationary. So what actually it is done, first of all I'll do some preliminary motion test with full load for which it is made. Okay, so this is the load test arrangement when I am testing with 3 kgs of payload which is here. Okay, all the motions will be tested. So now you can see almost all the actuators. Okay, so now this is a ferro tracker, ferro laser tracker. So that can remotely sense any point which is fitted at the top of this robot which is here from a distance. Okay, in its own frame it can do. That is in the measuring device. So this is your measuring device now. Okay, so now SMR is fitted here. Okay, spherically mounted retro reflector. So basically that is a spherical ball sort of thing that will be mounted here. Okay, So it is spherical in shape. So any light, if it comes to that, it goes back to the same direction. So similar is the case civil engineers, they do with theodolite apparatus also. Okay, so this is what is your SMR. So laser light is now falling from the ferro laser tracker, and that falls on this. So now I am measuring the floor on which this is mounted. This whole of this structure is mounted. Okay, and that is the ferro laser tracker, and this is my robot. I am mounting it here. Okay, so now it is fitted. Now you see SMR is fitted here. Okay, here is your SMR, that is the retro reflector. So this point is basically tracked. So that this point is nothing but it is the replica of the point which is also moved by the robot. Okay. Okay. Overall, there is a payload also which is fitted here. Okay. So now this makes this system complete. Now I am free to move. Whole of the thing is now placed properly, and this is the ferro laser tracker closely shown here. So while that point will move, this tracker will also move its laser pointer, and it will follow that pointer. Okay. So now a programmer sits here and he will command the robot to go to the plane, one of the plane of the robot, that is the cube arrangement that I have shown here. Okay. So this is the whole arrangement. Okay. So this is how it is fitted. Got it? So this is your SMR. Okay. So now I'll show you a small video. Okay. So you see the structure is moving, SMR is moving along with that. So all the corners of the cube, it is actually tracing. Okay. Starting from the middle point. Okay. And the ferro laser tracker will follow this point, record it precisely in its own coordinate frame, and that is used to calculate the repeatability. Got it? Okay, so hope you understood this, how this is actually done. Okay, so with that we'll end here, and in the next module we'll continue with robot control. That's all for today. Thanks a lot.